Hello and welcome to this video in the series Curly Arrows and Molecular Orbitals. My name is Nick Buurma, and in this series of videos I am going to talk you through the logic of curly arrow mechanisms in organic chemistry. In this video we're going to have a look at the so-called Beckmann rearrangement. I'm going to talk you through the Beckmann rearrangement on the basis of an old exam question that I've previously set. And you see the question over here. A reaction sequence shown below. We have a starting material that reacts with hydroxylamine and it forms an intermediate 2 which rearranges to form product P. And the questions were to draw a curly arrow mechanism for the rearrangement from 2 to form the product P, and the second part of the question was to draw a molecular orbital mechanism for this rearrangement reaction, and I asked to clearly identify the overlapping orbitals and indicate whether these are full or empty orbitals. So at this point, if you want to try to have a go at this question before I talk you through the answer, you should pause this video now and have a go. So let's have a look at the answer. So the first thing that you should hopefully realize is that the question asks to draw a curly arrow mechanism for the rearrangement from 2 to form P. And what that means that we are only interested in this part of the reaction. We aren't really interested in the conversion of the starting material 1 to intermediate 2. The reason why in this particular exam question I did give the first step for the reaction is that I basically told students, if you see some of these reactants, then you might be looking at a particular type of reaction. You might be looking at, in this case, the Beckmann rearrangement. So the first step was only provided in the hope that that might help more students recognize the correct answer to this question. But in practice, the only thing that we really want to do at this point is to draw a curly arrow mechanism for this particular step over here. So let's see how we are going to do that. So the first thing that we're going to do is we are going to draw the starting material again. Or actually, we're going to draw the starting material, but before we are going to carry out the rearrangement reaction, we note that the reaction is being heated and that this is under acidic conditions. And acidic conditions are normally applied if there is something in a substrate that needs to be protonated. So in the case of the Beckmann rearrangement, what needs to be protonated is this hydroxyl group over here. And what I'm going to do is I'll draw the curly arrows for this step. Curly arrows always start on a pair of electrons, so that's either a lone pair or that is a bond. In this case we're protonating the hydroxyl group, and that means that the curly arrow is going to start on these two electrons here, and a curly arrow always points towards a positive charge. So that's what's happening here. Curly arrow starts on these electrons and goes to something that wants electrons, in this case the proton. So if we now draw the result of this particular protonation, what I get is this protonated intermediate here. So if we're going to analyze, and you'll see that I like doing this, if we're going to analyze the curly arrows that we are looking at here, we see that these electrons move towards the proton, and that means that a new bond is going to be formed here. Do I see that in the intermediates that I've drawn after my reaction arrow? In fact, let me just add my reaction arrow over here. Do I see that new bond? Yes, that is this bond over here. And I see that none of the other bonds, nothing else has changed. I've only moved these electrons here, formed a bond. Another check that I like carrying out whenever I draw curly arrow mechanisms is to make sure that my charges make sense. So here I have a neutral substrate. I have added a proton, a singly positively charged proton, and what I get is an intermediate with a single positive charge. So I have a 1+ charge here, I have a 1+ charge here. That means that this protonation step looks fine. Okay, so now we reach the key step in the Beckmann rearrangement. What happens in the Beckmann rearrangement? It's a rearrangement reaction, so it turns out that this bond over here, again, I'm going to draw a curly arrow. My curly arrow is going to start at some electrons, and I have to choose which electrons they are. Now in this case, these electrons are the electrons that are in this particular bond here. So when I now draw my curly arrow starts on the bond. It starts on the electrons, and I know, because I've learned this mechanism, that these electrons move towards the nitrogen, and at the same time the electrons between the nitrogen and the oxygen move to the oxygen. So they go towards the positive charge. Okay, so both curly arrows start at electrons and move towards, in this case, an atom where the electrons are moving. Now you might be asking, how do I know that it's this bond that is moving, is rearranging? We'll see that in a minute in the molecular orbital mechanism. So we know that it's these electrons that have to move, not these ones. And on the next slide we see why that is the case. Why it's these electrons that move, not these ones. How do I know that, for example, the bonds in my aromatic ring don't move? Well, actually, one of the reasons is we'll see that they're not very well aligned in terms of the molecular orbitals. But the other reason as well is aromatic rings have aromatic stability. So if you can avoid breaking aromatic rings, you should really avoid breaking aromatic rings. You lose aromaticity. Losing aromaticity takes a lot of energy. Okay, so these are the curly arrows that I've now drawn. I'm going to draw my reaction arrow. And if I now draw what should be the product of this particular reaction, what I see is, if I start drawing from the left, I now have this nitrogen, but this nitrogen is now connected to the aromatic ring. Like so. My fluorine is here, the hydroxyl is here. It's still an aromatic ring, nothing has changed there. At the same time, I see that this carbon has lost its bond over here. Those electrons have moved to the nitrogen. These electrons are now this bond over here, and that means that there should be a positive charge over here, and at the same time I have formed a molecule of H2O. So let's do my analysis again. These electrons have moved here. That's now a new bond. There is no longer a bond to this carbon over here. That has become a carbocation. This CH3 is still intact. Aromatic ring is still intact. These electrons went to the molecule of water, H2O, so that became a neutral molecule of water. So this is indeed my intermediate. And the charge check, again, I had a single positive charge here. I have a neutral molecule and a single positive charge here. So my charge check on this molecule is fine as well. Now, what can happen in this next step is this molecule of water, or another molecule of water, of course, can attack this positive charge which leads to the following molecule. So you'll see that I'm going to rotate the aromatic ring a little bit again. So I will rotate that back to the way I drew it at the start of the question. So fluorine is here, the hydroxyl is here, but this atom is now connected to this nitrogen over here. This is still a double bond, and here I have a protonated hydroxyl group. Essentially, if I now take a base, that base can pick up this proton, these electrons go to the oxygen, and at this point I have this molecule here, and I have a protonated base. The reason I draw the protonated base on purpose explicitly is that I can now see that my positive charge has gone over here. I have a neutral molecule over here. So my charges make sense. Let's just make sure that everything else makes sense. I have nothing has changed here. I still have a single bond, a double bond, single bond to the oxygen. One of the protons is still here. This is the new intermediate. So in the final step of the reaction, which is a tautomerization, I will now turn this, which is essentially a tautomer of an amide, I'm going to turn that into an amide. I'm not going to explicitly draw the curly arrows for that. But my final product, P, is now this product over here. Okay, so that is the curly arrow mechanism. But the key step in the Beckmann rearrangement is this particular set of curly arrows over here, where the electrons in this carbon-carbon bond move to the nitrogen, and the electrons between the nitrogen and the oxygen move towards the oxygen to lose a molecule of water. So the next thing that we're going to do is we are going to look at the step that we see over here, and we're going to look at the molecular orbitals involved in that step, which will also explain immediately why it's this carbon-carbon bond that moves and not that carbon-carbon bond. So there we go. Here we go for the molecular orbital mechanism now. So what I'm going to do is I am going to draw the molecule again. Probably going to give myself a little bit more space. And some of the key parts of this molecule I am going to draw in a minute in a lighter color. And I had some protons on here and a positive charge. So in light blue there are bonds here and here, and the reason that they are important, if I add this proton here, and we'll have another look at this in a minute, but the curly arrows that I drew on the previous slide were essentially this. So what you see is that the bonds where things are changing, something is changing here and something is changing to this bond. And that's why I have drawn this bond as a dotted line and this bond as a dotted line as well, because stuff is going to happen to the molecular orbitals over here. So you can see that the curly arrow here starts on the carbon-carbon bond, and what that tells me is that the molecular orbital that has to be involved here is going to be a filled sigma orbital. I'll draw that like this. I'll draw 2 electrons in there. This is a filled sigma orbital corresponding to the C-C bond. You also see in the curly arrow mechanism that there is a bond that is going to be breaking here, and one of the ways in which you can break a bond is to fill the corresponding anti-bonding orbital, and that is what is happening in this example as well. So what I'm going to do here is I'm going to draw the anti-bonding orbital, the sigma star anti-bonding orbital that corresponds to the nitrogen-oxygen bond. So this is the empty sigma star orbital for the NO bond. Let me just sit to the side so you can see the word bond here as well. So what we see is that we have pretty good overlap between this filled sigma orbital and the empty sigma star orbital. So we have orbital overlap. Over here. So again, what we see is we see good overlap between the empty sigma star orbital for the NO bond and the electrons that are in the filled sigma orbital for the carbon-carbon bond can move, because of that overlap, into that empty sigma star orbital. Filling an empty sigma star orbital corresponds to breaking the corresponding bond, the corresponding NO bond, and that is exactly what we drew in the curly arrow mechanism. You can now also see how we know that it is this carbon-carbon bond that is going to move in the rearrangement, because the sigma star anti-bonding orbital over here has its maximum density in this region over here. So the overlap is a lot better with this carbon-carbon bond than with this carbon-carbon bond. So that's why the curly arrow starts here on the electrons, moves to the nitrogen, and it doesn't start on this side. The orbital overlap is good here and not here. Okay, so these electrons move, they form a new bond, and filling an empty sigma star orbital breaks the corresponding bond, exactly as we see in the molecular orbital picture there. So to stress that one more time, we have this system here. What we are getting is these electrons. Again, I start on the bond because that's where the electrons are, go to the nitrogen because that is where the empty orbital is, and these electrons are going to move to the oxygens. Again, I start the curly arrow on the electrons on the bond and they go to the oxygen. So if I look at that in terms of the molecular orbitals, that was my filled sigma orbital that has a good overlap. Just the oxygen. With the empty sigma star orbital, again, if I want to draw this as a curly arrow, I have electrons going from a filled orbital to an empty orbital. So curly arrows always correspond to electrons moving from a filled orbital to an empty orbital. So electrons go from filled orbitals to empty orbitals if there is good orbital overlap. Right, so that is the logic behind the Beckmann rearrangement. Beckmann rearrangement, the electrons go, arrows start at a filled orbital and move to an empty sigma star orbital, and that breaks the corresponding NO bond, and that is what this curly arrow represents over here. I hope that this has been useful. I'll try to make more of these videos. If you would like to see more of these videos, please leave me a comment, and if you have particular reactions you would like me to go through, I'll see whether I can do that as well. For now, thank you for watching, and hopefully see you for another video. Bye.